let's see the next type of a design issue that occurs in a concept of the pipelining, which is a structural hazards. This lecture we are going to talk about what is a structural hazard, what are the examples of structural hazards, and we will also see how to resolve the structural hazard situations. So coming to the introduction, in the previous lecture we have already discussed about one of the design issue which occurs in pipelining, which is the data hazards, and we have also seen the examples of data hazards and how to resolve the data hazard situation. So the other type of a design issue that occurs in a pipelining is a structural hazard. So structural hazard is nothing but it is a situation when two or more instructions they require the use of a same hardware resource at the same point of time. So structural hazards is something with respect to the hardware resources. So when multiple instructions are going to access the hardware resources, if there is only one hardware resource, say for example a memory, so in that case, when multiple instructions are trying to access a memory at the same point of time, then it leads to a structural hazard situation. So structural hazards occurs mainly due to the resource conflicts, unavailability of resources, or due to less amount of resources. There will be conflicts between the instructions which are being executed simultaneously in the pipeline. And if you consider the most common case in which a structural hazard situation arises in the pipeline is in terms of accessing the memory. When multiple instructions are trying to access a memory at the same point of time as a part of their execution, it leads to a structural hazard situation. Say, consider one instruction access the memory as a part of performing a write back stage. So, where it has to write the result into the memory at some location in the memory. Say, other instruction at the same point of time, which is simultaneously executing in the pipeline, as a part of its fetch stage, it has to fetch the instruction from the memory. So, both these instructions require to access the memory at the same point of time. But there is only one input port available for the memory. So only one instruction can access the memory at a one point of time. So because of which only one instruction is allowed to access the memory, which leads to a structural hazard situation between these two instructions. So to overcome this situation, many processors they use a separate instruction and data caches to avoid this delay. So here the first instruction is accessing the memory as a part of writing the data into the memory, whereas the second instruction is accessing the memory in order to fetch the instruction from the memory. So as we know, both the instructions and data, both of them reside in the same memory. So if you have separate instruction cache and data cache available with each having their own ports, then type of structural hazard situations can be eliminated. So let us see an example of a structural hazard where load x of r1 comma r2. So here the memory address x plus r1 we are going to compute it, and then you are going to access whatever is the result, that particular memory location is accessed, and that particular operand is read from the memory and written into the register r2. So let us see. So here the instruction I2 is a load instruction. So the instruction is going to compute the memory address x plus r1. It is computed in a E2 stage, and the memory access, it is going to access the memory for the particular operand in clock cycle 5, and the operand is read from the memory and written into the register R2 in clock cycle 6. So this means that the execution step of this particular instruction, it is taking two clock cycles, cycle 4 and cycle 5. So it causes the pipeline to stall for one clock cycle because both the instructions I2 and I3 requires access to the register file at the same point of time. So here, because the memory access of the instruction I2 is happening in the fifth clock cycle, since the I3 instruction is also simultaneously executing in the pipeline, it fetches the instruction in clock cycle 3, decodes in clock cycle 4, and executes in clock cycle 5. But to perform a write back in clock cycle 6, in a clock cycle 6, the write back stage of I2 is taking place. So it cannot access the memory to perform a write back in clock cycle 6. So the write back stage of instruction I3 is delayed until the clock cycle 7, because the register file cannot handle two operations at once. So it cannot handle I2 and I3 at the same point of time.
So if the register file has two input ports, it can allow two simultaneous write operations. So the pipeline would not have been stalled. So in this situation, how can you overcome or how can you resolve the structural hazard situation is by having two input ports, more than one input port for the register file to perform a write operation for two instructions at the same point of time so that the pipeline would not be stalled. So the structural hazard situations overall can be avoided by providing sufficient hardware resources on your processor's chip. So in order to implement the concept of pipelining, overall you need to have enough amount of hardware resources available on your chip which is capable of executing simultaneous instructions at the same point of time. And the pipelining does not result in the result of the pipeline does not depends upon the individual instruction being executed faster. It is the throughput that matters. If you see at some point of time, the throughput of that particular process have to be increased. So what is throughput? It is nothing but the number of instructions which are executed per unit time. So it is not about the individual how long is the individual instruction which is being executed. The concern is the throughput of the processor has to be increased, which is nothing but the number of instructions which are executed per unit time has to be improved. So at any time, one of the stages in the pipeline cannot complete its operation in one clock cycle. The pipeline stalls and the performance of the pipeline degrades. See one more example of a structural hazard. So it will have a machine which has a single memory pipeline for both the data and instructions. As a result, when an instruction containing a data memory reference load, it will conflict with the instruction for later instruction, which is instruction 3. So consider there is a memory, single memory for both the data, but storing both the data as well as the instructions. So because of which we have a load instruction which is accessing the memory because in order to load the particular data, and we have one more instruction I3. So if you consider this, the load instruction is going to perform memory access in fourth clock cycle in order to load the data into the corresponding registers. And at the same point of time in the same clock cycle 4, the instruction I3 is also going to access the memory as a part of its fetch stage. So we have only single memory which stores both the instructions and data, but we have two instructions which are accessing the memory in the same clock cycle. So because of which the structural hazard situation occurs between these two instructions load and instruction 3. So how can we resolve this situation? So in order to resolve this, we are going to implement the concept of pipeline bubbling or pipeline stalling technique for one clock cycle whenever there is a structural hazard situation between these two instructions. So rather than executing this particular instruction I3 in the fourth clock cycle, we are going to bubble or stall the pipeline for one clock cycle so that in the next clock cycle the instruction I3 will be fetched and executed. So that this particular structural hazard situation is resolved in the pipeline. So you can also represent it like this. Instruction I1, I2, I3 for fourth clock cycle you are going to stall it, and from the fifth it starts its execution. You can represent the pipeline in this manner, bubbling, or you can simply implement a stall in this clock cycle and start the execution of the I3 instruction in fifth clock cycle. So here we are stalling the instruction I3 to resolve the structural hazard situation. So here when you are introducing the stalls in order to overcome the structural hazards in a pipeline, so if the number of stalls is minimal, there is no problem. But you keep on using more and more number of stalls in your pipeline, it degrades the performance of your system or it degrades the performance of your pipeline. But still, the designers of the processors, they still allow the structural hazards for two reasons. The first reason is to reduce the cost. So rather than providing additional hardware resources, which for a normal processors, for a high-end processor, this is not acceptable. For a normal general processor systems, you can still allow the structural hazard to some extent. Next is to reduce the latency of the unit. The shorter latency comes from the lack of pipeline registers that it introduces the overhead. So for these two reasons, the designers of the processor still allow structural hazard situations. Thank you.